But it's a great pleasure and a great honor to have here Miklos Rasonyi. I know Miklos for many years now. It's a fantastic colleague. He spent some time in the UK, but somehow he decided to leave us to go back to Hungary. He is now a senior figure at Renyi Institute of the Hungarian Academy of Sciences. He is a person that worked a lot with algorithms, of course, and with probability theory, mathematical finance as well, but mainly when it comes to understanding algorithms and Markovian processes, is one of the key persons in the field. So, with great pleasure, we're going to hear the talk, rate estimates for total variation distance. Miklos, thank you so much. The floor is yours.
Okay, thank you, Sotirios. The bad news is that this is a strongly mathematical talk. The good news is that it will not be 1 hour long, I promise. So it will be significantly shorter. And I'm starting it quickly. So I'm interested in situations where we know weak convergence, but we would like more. We would like to have total variation convergence. And it is about a method that works in many interesting cases. You will see some examples. I will first talk about normal approximation, because this is the case where everybody is using weak convergence. Then I will draw some examples from Malliavin calculus, where there has been some recent progress related to this kind of problems. And then I will talk about the present research, and I will give examples outside machine learning, and finally I will give some examples from machine learning. Let me go further. So, some mathematical definitions. Wasserstein metric, everybody knows this. For p equals 1, you know that there is an alternative characterization using Lipschitz functions with Lipschitz constant smaller than 1. Total variation is also well known. Slightly lesser known metric is the Forte-Mourier metric, which is again this kind of supremum of differences, but the set of functions is those which are bounded and their derivative is also bounded by 1. It turns out that this is a useful metric for weak convergence. This is convergence in this metric is precisely weak convergence. Okay, and finally, I mentioned weighted total variation norm, where we also have some power of the random variables involved, and we would like to estimate this and total variation norm. And I also mentioned Kullback-Leibler divergence. So, in machine learning, there are lots of estimates using this Wasserstein metric, and there is recent progress for diffusions. For example, by Andreas Eberle, who is no longer here, but he was around. And also for SGLD schemes. Total variation is used a lot in Markov chain theory in Main and Tweedy book. You find total variation estimates. Forte-Mourier metric, it's also quite useful in contractive stochastic systems. You will see an example later. And there are many situations where we don't have total variation estimates. Let me see some typical examples. The Berry-SAM theorem, it gives you the speed in the central limit theorem. So we have IID, zero mean random variables in RD. We need a finite third moment, and we look at the normalized sums. And we all know that this converges to this, where phi is the standard normal distribution function. This is well known, but Berry and SAN in the 50s obtained this. This is their famous theorem. Later, with finer methods, you can even get Wasserstein 1 distance. If you go to arbitrary D, the situation is less complete. So in Forte-Mourier metric, you have got this in full generality. So this is true. And under additional conditions, you have Wasserstein one. But for example, as far as I know, this is not completely characterized. So we don't know in what generality this result is true exactly. Okay, and in the one-dimensional case, but as far as I know, only in the one-dimensional case, you have total variation convergence, but you need strong hypothesis on the summons, on the X. And also sometimes you can get this in Kullback-Leibler divergence. Now I will switch to seemingly distant topic, which is Malliavin calculus, because interestingly, they obtained made some progress in the framework of Malliavin calculus. So they can have better results if the functionals involved come from the Malliavin space, from the Wiener space. Okay, so what is Malliavin calculus? I will tell you in 2 slides, but so it's a bit sketchy. So it's differential calculus for functionals on the Wiener space. For example, if you take some smooth function of the increments, that's certainly a smooth functional. But the good thing about Malliavin calculus is that using functional analytic techniques, you can define certain Sobolev type spaces, which are much, much bigger. So they contain, for example, the maximum of a Brownian motion. It's also a functional which is Malliavin differentiable. So many functionals turn out to be Malliavin differentiable. And the main tool here is a certain integration by parts formula, or there are infinitely many of them actually. So these formulas. And the typical results are about absolute continuity of functionals, smoothness, positivity, tail estimates. And we should not forget that the solutions of stochastic differential equations, they are Malliavin differentiable if the coefficients are differentiable enough. And in this field, there has been some progress about total variation convergence. Namely, there is a book by Nurdin and Peccati, which received some prize at the time when they published it about 10 years ago. They prove total variation convergence in central limit theorem for certain Malliavin functionals. They also have some non-central limit theorems. All this is very nice. And then it was further developed by other authors like Bali and Caramellino. And I will cite in a very sketchy way some of these results. So I will skip the fourth moment theorem. So a typical theorem is the following. Let us take a sequence of functionals which are twice differentiable in this Malliavin sense, and all of their derivatives have a fourth moment. So this is a typical Sobolev type space. And they are zero mean, they have variance tending to zero. If the sequence of derivatives is bounded in L4, and the fourth moments of the second derivative tend to zero, then this sequence approximates standard normal law. This is not the most general theorem they have more interesting ones, but it shows that basically if you have a sequence with some smoothness properties, which has to be defined in a suitable way, then you can have, instead of simple weak convergence, you can have something stronger. And then Bali and Caramellino have the following results, also with another coauthor, Poli. This is the other one. This says that if you have 3 times differentiable functionals that are uniformly non-degenerate, I will not define what it is. If these are solutions of stochastic differential equations and these are uniformly elliptic, then, for example, these are uniformly non-degenerate. But it's a more complicated notion. So, for such functionals, convergence in total variation is implied by convergence in Forte-Mourier metric. So from weak convergence, you have a direct link to total variation convergence. You need to assume smoothness, some moment conditions. So you need things, but after all, in the context of Malliavin calculus, these are not strong assumptions. Then they managed to fortify this. If you have infinite smoothness, then actually you can get 1 minus epsilon here. So you almost get the weak convergence rate. And this gave me the hint to try to do something without Malliavin calculus, which can apply, for example, to rates in algorithms, in stochastic algorithms, such as the stochastic gradient Langevin dynamics. Can we have convergence guarantees in total variation using existing convergence guarantees for Wasserstein metric? Okay, so the objectives, we have a convergence estimate in Wasserstein metric or Forte-Murray metric. We want a rate in total variation or weighted total variation. And we know that there need to be smooth densities. So we need some smoothness here for this to work. We want an add-on approach. It means that we do not want to prove total variation convergence from scratch. We want to have a method which fortifies an existing, which strengthens an existing result to total variation. We want something which is a method, which is not a one-time solution, which works in discrete-time stochastic systems, and which is without Malliavin calculus. There is this mysterious or little. What I mean is that what we are doing seems to have some implications for Malliavin calculus itself. So it can be used in Malliavin calculus to strengthen certain results. So if we want to prove that in Malliavin calculus, we obviously need some Malliavin calculus, but not much. We need elementary Malliavin calculus plus this analytic and probabilistic method, which I will talk about. Okay. First, let us see a stochastic system which is driven by colored noise. This is not machine learning, but it's an interesting stochastic system. So this is an infinite moving average process, like an ARMA process, something like that. And we are looking at a dynamical system which is driven not by white noise, but by this colored noise. And we would like to see if this has a limiting distribution. This is old stuff. I don't know. It certainly goes back to the 70s or the 60s. So it's very easy to prove this. It's half a page or less. That if this is contractive, then even if we feed in a colored noise, we will have a limiting distribution. And in Wasserstein metric, you get this exponential rate. If you don't have contractivity, then this is a very deep question. So the only result is by Heirer and by people who were building on his work, and it's extremely complicated. So if you don't have contractive condition, if beta is only dissipative, say, then there are some results for Gaussian noise, but it's really horribly difficult. And so what I'm doing is something much simpler, but still it's non-trivial. So if the density of epsilon zero is the white noise which builds up this colored noise Z. If that has a density which is d plus times differentiable and they are integrable, then this is strengthened to total variation convergence. So this is the type of result I would like to have also in the machine learning context. Okay, there is another result under weaker conditions. We only have weak convergence. Sorry, but that can be strengthened under not too complicated conditions. It can be strengthened to total variation convergence. So it works in more than one case. Okay, now let us turn to the main topic. As I promised, I will not be long. Now comes machine learning algorithms. there has been several talks mentioning the Malliavin equation. So this is one more talk where this is mentioned. We take B to be measurable. W is a d-dimensional Brownian motion. We assume that B is Lipschitz and it's dissipative in this sense. This is scalar product. And this is obviously much weaker than being the antiderivative of a strictly convex function. And on this equation and on the related discrete time schemes, there are many recent results. There are especially these nice symmetric, Wasserstein symmetric estimates, but I will not talk about that. I will just mention that under such conditions, so this diffusion has a limiting distribution, and if B is the gradient of something, then this limiting distribution is e to the minus u, is proportional to e to the minus ux. And we can try to sample from pi using the well-known Euler scheme. The discretization error is known to be square root of lambda. In cases it can be lambda, but let us stay with the square root of lambda. So I mentioned one typical result. There are really many similar results. I took this result from the paper by Mijatovic, Majka, and Spruch, but they build strongly on the previous paper of Eberle and Majka. It's a typical example in Wasserstein metric. Let us consider this Euler scheme. We assume that B is Lipschitz, and it has this contractivity property outside the ball. I once wrote in one of our papers that it's convex outside the ball, but then we realized that this makes absolutely no sense, that something is convex outside the ball. So no, it means that on a large scale it behaves like a convex function. So this is the formal this is the rigorous formulation. And what they can prove is that for lambda small enough, the error of this scheme is of the order square root of lambda, as I said, and yes, and there is an exponentially decreasing term in n, and the exponentially decreasing term nicely scales with lambda, because that is the non-trivial part, that it nicely scales with lambda. I'm not saying that otherwise it's trivial, but otherwise it's much simpler. And C1 may depend on the initial value. So this is a typical result. There are many such results in total variation norm under certain conditions, but I chose one in Wasserstein metric so that I can use it as a demonstration of our method. And finally, this is our common work with Eric and Sotirios and Ying, and with the former postdoc of mine, Yu Chao, that we have a convergence guarantee for the stochastic gradient Langevin dynamics if the unbiased estimate of the drift is H, it is Lipschitz, it is dissipative, then for lambda small enough, we have a convergence guarantee in W1 metric with the optimal rate. So this is another result which is in Wasserstein metric, but it gives a rather strong convergence guarantee, because square root of lambda is the optimal. You cannot do better. What are our standing smoothness assumptions? So we need smoothness. We assume that U and H are C infinity. B, the gradient, obviously B is also C infinity, but the derivatives of B are also bounded. B itself is not bounded. It should be linearly growing, something like that. We need moments of all orders for the initial conditions. We can have results under weaker assumptions, but we did not go into that. So if we have only 5 times continuously differentiable functions and fifth moment, then we get something weaker. But this is like the strongest conditions. And This new result is not really new, I will tell you. This is only using the previously cited result in Wasserstein one metric by Mijatovic, Majka, and Spruch. We can get and ameliorate the result in total variation norm. We lose a little bit in the rate. We lose an epsilon in the rate. I'm saying that this is not a new result because it is known that this is true. But this is first a new proof. And the second, in that result, the rate is not explicit. In that result, one needs to use the rate of the continuous diffusion, and that is quite difficult to estimate. So it's very far from being simple. It's not impossible to estimate, but what I'm saying is that to calculate the constants in that theorem, you should make a real effort. But in this theorem, you don't have to make an effort because the constants of Mijatovic, Mateusz, and Spruch are explicit, and I only have to multiply them with my constants, which are also explicit. So it is easier to get it. But this is a little new result. The real new result is about the stochastic gradient Langevin dynamics. So under the same conditions, plus these smoothness, strong smoothness conditions, we can have an estimate in total variation norm, and we are working on extension to weighted total variation norm, but that is not yet done. And this is very much work in progress. No, there is no preprint yet. So I cannot share with you more details at this point. I hope it will be ready by Christmas. And let us draw some conclusions. So we want to get some general tools which may work for diffusion models, discrete numerical schemes, and these machine learning algorithms. We also would like to apply our results to Malliavin calculus and to normal approximation, and this seems to work also, but it should be the topic of another talk. This may help to obtain consistency and central limit theorems for SGLD schemes. When I wrote this, I thought this was true. It still might be true, but now I have better ideas about this. So I think this consistency and central limit theorems has to be done differently. After I talked to Andreas Eberla, I changed my opinion on this point. And okay, and if we manage to do that, we will go to Mars and Ceres, and we will build universal happiness on Earth so that everybody will just sing and dance. And the talk is over at this point.
What an amazing message at the end. Thank you so much. Last time to speak here. And given the fact that that was a long week, finishing so early, we are very grateful, Miklos. But okay, if there are any questions, we're happy to take a question or two. Here it goes, our first question. Tim.
Thanks for the talk. The bound you got on total variation, is this anything to do with the bound? You can bound total variation, right, by Wasserstein on a, if your state space has a bounded radius. Is that not true?
No, it's true the other way around.
Oh, it's the other way around. So you bound Wasserstein by total.
What you can do is that you can always bound Wasserstein by weighted total variation. Okay. That is feasible.
Mm. But did you use that principle for that result that you showed? Did you use the Wasserstein bound to prove the result in total variation you presented?
No.
Okay. Yeah. Okay, that's great. Thank you.
But he's not willing to reveal many secrets, I guess, because the paper is not ready. Next question.
Thank you so much, Miklos, for the talk. I want to ask because I think we have the result that in V total variation, the Euler algorithm also has this rate under very weak condition. So here is for, because we see the rate is 1/2 minus epsilon. Is this epsilon here because we have the SGLD algorithm? We have the stochastic gradient, so we lose some power there.
I don't precisely understand. So the question is whether we can do something about the epsilon. For the moment, no. So what I can tell you is that actually, because everything is very nice, so we have a smooth normal density, I conjecture that this can be made even better. It can be made square root of lambda times the logarithm of lambda absolute value at some power. I think this is doable, but already this is not simple. So I think that's the limit of this method. So we cannot do square root of lambda, but we could do square root of lambda times logarithm of lambda at some power. That I can imagine.
Great. Any other questions? Ah, there is one. Wait, Miklos. Wait.
Thank you for your talk. I just want to ask a basic question about the definition of Forte-Mourier metric. The difference with Wasserstein 1 is that it's also assumed that F is bounded. What's the main difference with?
You take F, which are bounded by 1, and whose Lipschitz constant is bounded by 1.
But by shifting isn't...
I mean, not Lipschitz constant, whose derivative, sorry.
So it implies that it's also Lipschitz if it's gradient.
It implies, so, but the two things are on RD, the two things are the same. So I could take one thing, so it gives the same metric. If you take F such that its derivative is smaller than 1, you get the same metric as if you took all the Lipschitz continuous functions which are bounded by 1. But if you are on another state space, which is not a Euclidean space, then you can't talk about Forte-Mourier metric because there is no differentiability. You can always talk about bounded Lipschitz functions. So with bounded Lipschitz functions, you can always define this object on anything that has a metric. But Forte-Mourier works on a space where you also have differentiation.
I see. Thank you.
So it's sometimes called bounded Lipschitz norm. That's a bounded Lipschitz metric. But well, in the literature, in Malliavin calculus, they prefer this Forte-Mourier formulation with the derivative.
I see. I thought because without loss of generality, by shifting, we can assume that it's bounded all the time. Isn't that the case?
Yes, but it may change the metric, but it doesn't change the convergence. So it remains the same story.
I see. Thank you.